Key concept 3.3. Efficiency of big Y bar. Big Y bar is capitals BLUE. Blue. It spells. Let mu sub big Y hat be an estimator of big Y, of mu sub big Y. That is a weighted average of big Y sub 1 through big Y sub n. That is mu sub big Y hat equals open 1 over n close sigma from I equals 1 to n of a sub I big Y sub I, where a sub 1 through a sub n are non-random constants. If mu sub big Y hat is unbiased, then var of big Y bar is less than var of mu sub big Y hat, unless mu sub big Y hat equals big Y bar. Thus, big Y bar is the best linear unbiased estimator. Blue, that is big Y bar, is the most efficient estimator of mu sub big Y among all unbiased estimators that are weighted averages of big Y sub 1 through big Y sub n. Returning to the text, the estimators big Y bar, big Y sub 1, and big Y tilde have a common mathematical structure. They are weighted averages of big Y sub 1 through big Y sub n. The comparisons in the previous two paragraphs show that the weighted averages big Y sub 1 and big Y sub tilde have larger variances than big Y bar. In fact, these conclusions reflect a more general result. Big Y bar is the most efficient estimator of all unbiased estimators that are weighted averages of big Y sub 1 through big Y sub n. Said differently, big Y bar is the best linear unbiased estimator. Capitals blue, it is the most efficient, best estimator among all estimators that are unbiased and are linear functions of big Y sub 1 through big Y sub n. This result is stated in key concept 3.3 and is proved in chapter 5. Big Y bar is the least squares estimator of mu sub big Y. The sample average of big Y bar provides the best fit to the data in the sense that the average squared differences between the observations and big Y bar are the smallest of all possible estimators. Consider the problem of finding the estimator m that minimizes the sum of I equals 1 through n of open big Y sub 1 through m. Restarting. The sum of I equals 1 through n of open big Y sub I minus m close squared equation 3.2, which is a measure of the total squared gap or distance between the estimator m and the sample points. Because m is an estimator of big E of big Y, you can think of it as a prediction of the value of big Y sub I, so the gap big Y sub I minus m can be thought of as a prediction mistake. The sum of squared gaps in expression 3.2 can be thought of as the sum of squared prediction mistakes. The estimator m that minimizes the sum of squared gaps big Y sub I minus m in expressions 3.2 is called the least squares estimator. One can imagine using trial and error to solve the least squares problem. Try many values of m until you are satisfied that you have the value that makes expression 3.2 as small as possible. Alternatively, as is done in Appendix 3.2, you can use algebra or calculus to show that choosing m equals big Y bar minimizes the sum of squared gaps in expression 3.2, so that big Y bar is the least squares estimator of mu sub big Y.